Hi, this is Owen from Hands on Deck. This is my family's 2012 SL trim Nissan Leaf. Leaf stands for Leading Environmentally Friendly Affordable Family Car. It was the first electric car produced for the mass market in the whole world, and this specific year's model came with a 24 kilowatt-hour traction battery. But more than a decade later, it's been struggling to get places. On a good day with a full charge, the car can run about 40 miles at most before grinding to a halt, and in frigid temperatures with unideal weather, it is a lot less. For daily commuting purposes, plugging it in whenever possible is necessary, and has become a very local car. Faced with these issues, one might think that we should scrap the original car and get a newer model instead, but it's important to note that the only thing that is degraded on this vehicle is the battery itself. The state of health is at around 60%, but the rest of the car runs just fine and is in almost perfect condition. Since 2012, Nissan has updated the traction battery's capabilities. First, they added the 30 kilowatt-hour specification in 2016, then the 40 kilowatt-hour in 2018, and finally the 62 kilowatt-hour in 2019, which is capable of running for more than 200 miles off a full charge. To demonstrate what an electric car can do for us with regards to sustainability, reliability, recyclability, and especially energy efficiency, I've decided to initiate this long-term project, with the very first stage to switch out the traction battery from a 24 kilowatt-hour battery to 40 kilowatt-hour one, and keep it on the road for hopefully many years to come. Next, I can take apart the original battery cells and, keeping the ones that are in good working order, use them as a stationary power source for my own household use, like how Tesla Powerwalls did for home energy storage solutions, which used brand new lithium-ion batteries. However, most people who have worked on a job like this one require a car repair shop, one that includes all sorts of heavy equipment, such as car lifts, a forklift, maybe some specialized repair equipment like a heavy-duty battery lifting cart. That alone can cost thousands of dollars. There are also some other DIY attempts out there, but said schemes are quite risky, and to put it lightly, there are safety concerns all over the place. In my view, there should be a better yet smarter and safer yet affordable way to do the battery switch, such that even a young high schooler can handle it himself. By the way, I hope this can also serve as an advocate to all the car makers out there to consider swap-friendly battery systems in future EV designs. So here, I'll show you the process I designed after many years of research, planning, and of course many mistakes and end-of-the-line situations. One only needs some basic tools that are either already in the toolbox or are easily obtainable for every home. Nevertheless, I have to emphasize that you have to know what you are doing for each step and have a comprehensive understanding of the whole plan's design and process. You also need to know some basics of both the car's electrical and mechanical systems. So, please be patient and watch the whole thing before deciding if it is the right job for you. Whether yes or no, you are more than welcome to contact me with any questions and for help. I would love to share my experiences and extend my assistance to those who need it. Now, first things first, I have here an acquired 40 kilowatt-hour battery sitting here, stripped off from a total 2019 Nissan Leaf. The acquisition of a good replacement battery is another long story that I might talk about later. It took me, quite literally, many years. Its current state of health is beyond 90%, which is pretty good. Next, I will jack up the car, take the old battery out using the height-adjustable carts that I improvised, the key to our whole design, and then switch out the old battery onto those carts. After that, we need to put the new battery on them, roll it under the car, and raise it into the battery bay. With this plan, we should be able to pull this off without needing any heavy machinery. Let's get started. An electric vehicle is generally heavier than an internal combustion engine car of the same size. The reason is because of the battery. Therefore, I need a crane to help me move around the two batteries involved here and do the switch. Unfortunately, the drained battery still weighs about the same. It's kind of an interesting point that we'll come back to in the later stages of this long-term project. Just be patient. This is the one I decided to go with. Interestingly enough, this simple crane is made to lift an ICE engine, and is more commonly known as an engine hoist. It arrived in a huge box, and I spent an afternoon and a morning assembling it. The choice of the specification is based on the weight of our traction battery, thereupon tripled and quadrupled, just to make sure it could never ever go beyond our safety envelope and to always have more than enough redundancy in the whole process. This crane specifically can support 4 different maximum weights, from 1 ton to 2 tons, depending on the crane's arm length, and it is a manually operated hydraulic model. In most parts of the country, you can rent this by the day, which would be the best solution, provided you can do the whole thing in about a few hours, if you prepare well enough ahead of time. I bought mine with a sales price of about $150, since I will need it in several later stages of my long-term project. Here's a demonstration of raising the crane to the maximum height, and lowering it. Some other tools are required in this design. We need 2 height-adjustable carts to move the battery out from under the car. As I said before, this lift is the key to my design. The lift itself is made for motorcycle repairs, and the manufacturer provides a cart to add mobility to the lift, which makes it the perfect battery cart. Considering the size of the battery and that of the cart, we prepared 2 of them to share the weight of the traction battery equally. The choice of specification is important here too. I chose a 1,000-pound max support model to make sure it's absolutely safe whenever and wherever I move the batteries. With a 2,000-pound support capability in total, we are looking at again 3 or 4 times above the actual battery weight. The cost for each cart was about $50 to $60 each. For an Amazon deal of about $50, I got an electric hydraulic jack to lift the car up. It's much easier to use than a manual jack, and it can work together with the battery carts that I got to roll the battery in and out. Straps are also necessary to hold the battery down to the carts, so the battery doesn't slip or move. The specification for the straps is also about 1,000 pounds. Jack stands hold the car up to a specific height. This is a safety must, and it also gives enough clearance under the car for battery movement. We also need a translator system to make the car recognize the new battery and be able to drive with it. Here is a list of other important tools that are generally used for mechanical repairs and switches, and some that I used. Note that high voltage work gloves, clothes, and shoes are important for safety, and a flashlight is very helpful for seeing under the car. Before doing anything, we must remove the fuse socket of the traction battery. Only when this is done can we proceed with following all of the remaining steps safely, and only then do we not need to worry about the 380 volt potential difference. Wearing proper PPE is also important here too. I initially tried to raise the car with a manual jack like so. However, the amount of effort that it took was excessive. The weight of the battery and the car takes its toll as we jack the car up and down. In comparison, the hydraulic jack was much easier due to the flatter platform here. It's powered with alligator clips that connect to the car's 12-volt battery. I raised the entire car by around 17 inches. To get at the battery on the bottom, use a screwdriver or a drill to unscrew the screws that secure the plastic covering to the car chassis, and a hammer to pull the plastic push-ins out. These can be fragile after many years. After this, however, you should be able to see the battery underneath. There are 3 of them that are necessary to take out, helpfully labeled 3N2, 3N3, and 3N4. The arrow points to the front of the car. After such a long time, 12 years, many of the plastic push-ins and screws are completely worn out, so when I put them back in once everything is done, I will use some new ones that I bought. It's also helpful to keep track of which screws were used where. Position the carts here such that they are under the 3 main steel beams baked into the battery. I measured the height of the carts beforehand to make sure I raised the car high enough. Place a wooden board on top of the carts to allow for stability. Make sure they don't cover the 6 main bolts, as we'll have to remove them once the carts support the weight. Slowly raise the carts to meet the battery. Remember to remove the equipotential lines too. Before unscrewing the main screws that hold the battery up, remember that the battery is also connected to the frame in the back through 2 plates with 2 screws, like so. You may also choose to unscrew them completely from the top and pull them back to prevent them from colliding with the battery when you lower the old one or raise the new one. A torque wrench is recommended here, especially for a car like this which is run over a decade. We all know EVs are intrinsically low maintenance, which means that over a decade, most of the screws, bolts, etc. have never been touched since the car was manufactured and the parts were installed. So, both the torque wrench and the impact wrench were necessary for removing screws, and I ended up using both throughout the whole process. These 6 bolts are the main bits holding the battery up. Getting them out took a lot of persistence with the impact wrench, working so hard that the metal became hot to the touch. It also tested the virtues of patience. And after 12 years, the rust really showed. Using the proper PPE, disconnect the old battery from the car. Care is required due to the number of small parts involved. The smaller port here also requires an initial counterclockwise turn. The wood blocks are ready to position between the raising mechanism and the car itself, so that if something fails when lowering the battery, nothing will crash down and injure someone. Once again, the power drill comes in handy in lowering the car and the battery down a few centimeters at a time, keeping the battery in a level position. This is also very useful when I raised the new battery, and it was a happy and unexpected convenience that turned the manual lifting process, which was very strenuous, into an electric one that only required a bit more attention. Such a lucky idea. It's worth mentioning the high torque requirement for the power tool is absolutely enormous, especially when the cart is low to the ground. I would highly recommend a corded drill rather than one that is cordless because it gets very hot incredibly quickly and the battery drains out fast. I had to put on a cooling pack to extend its output. Luckily, it still worked. Ratchet tie-downs are incredibly helpful here for securing the battery. Each one of these is also rated up to 1,000 pounds as well, as part of the system design and redundancy planning. Making sure the wheels are facing the right direction, I, like in a game of tug of war, pull the old battery out slowly. To be honest, it was a bit easier than I expected. For the crane to be able to pick up the battery, I have to raise the carts slightly.
Note the use of the power wrench again.
The old battery can now be lifted with the crane. I have set the weight limit to 1.5 tons here. An interesting anecdote. It was trash collection day when I did this. The truck driver saw my setup and came to talk with me, and after I told him all about what I was doing, he commented,
"After finishing this, you can do anything."
I thanked him for the encouragement. These recycling bins are made of rather thick plastic, and I could even stand on them without them sagging at all. With the help of some 2x4s, the entire setup could be made more stable. Here, I lowered the old battery onto the setup. It's a case test by itself for the structural integrity of the recycling bins. While a bit unconventional and slightly unreal, the design works, and I didn't have to implement my crazy backup plan for what to do after a potential collapse. The new battery is on this cart, and after a cleaning session, it looks ready for loading. Note, the newer batteries have a PTC, positive temperature coefficient, power connector to heat the battery, but the 2012 vehicle cannot take advantage of this. Hopefully in the future, ECM software will enable this, but right now it's not an urgent task, so I capped it here. I load the crane and thread the orange straps here so I can lift the new battery. The 40 kilowatt hour battery is 668 pounds, only a bit heavier than the 24 kilowatt hour one, which is about 648 pounds. This proves that energy density has increased quite a bit, likely because Nissan, when first making the Leaf, put in a lot of effort to make sure the entire system was as safe and redundant as possible. We lower it onto the carts, and we retie them down with the ratchet straps. We can now lower the cart again, Before reconnecting the battery, we need to set up the translation system so the car knows the battery exists and it runs with it. The translator itself requires a B24 adapter and a cam bridge. I also zip tie the cables so they are more secure. We utilized Muxin's cam bridge by Emil Nissan. I've been following his work for many years and he did a superb job with the coding. Thanks to him for making his code open source. Now I have to push the battery under the car. Positioning the battery right below the battery bay is actually a harder task than meets the eye. I ended up using the laser to pinpoint the exact position where every bolt should go. Now with the new battery in position, we can raise it. I made sure that nothing else was in the way, especially the two plates in the back. This bit took more effort because of the greater weight. Now it's time to move the bolts in the back into position. Now it's time to reconnect the battery, this time with some additional adapters. Note the importance of PPE again, and go slowly. Now we can put the 6 main bolts that hold the battery up back into place.
Before installation, I added some Permatex anti-seize lubricant to the bolts, so it would be easier to get them out the next time I change the battery. Ready? 3, 2, 1. Nice.
Now the new model and battery design are different from the original underbody coverings because the positions of the fasteners have changed. As a result, I have to drill new holes in the original covering before I can install them on the car. 7 of the screws on 3 and 4 cannot line up with each other under the car. But after the drilling's done, we can put all the plastic coverings back. I acquired the high voltage fuse socket that came with the new battery, and now I have completed the connection. to double check, we reconnect the 12-volt battery, and now for the moment of truth. It seems like the car starts. So now we can finally lower the car down. And so, we are done. We ran the battery down and fast charged it. On a full charge, the dashboard reached 149 miles and 164 miles on eco compared to a max eco of 55 miles in the past, which even then was an overestimate because, in reality, it was only 40 miles. Above all, I still get a very impressive energy efficiency performance, nearly 4 miles per kilowatt hour, which is all that matters. Note that the bars on the top are only accurate when attached to a charging station, which overrides the car's computer because the car's computer can only display battery capacity from 0 to 60% accurately. Again, because it ranges from 0 kilowatt hours to 24 kilowatt hours, it doesn't know anything above 24. That's another side project we can do at a later time. I'm happy that this completed project has proved that the design ideas I had over multiple years of desk work seem to have been proven correct. I also cannot emphasize enough, however, how important it was to leave more than enough redundancy in every detail of an engineering design. But now we have a fully functional 2012 Nissan Leaf with a 40 kilowatt hour battery. For daily commutes and the occasional long distance drive to a nearby city, it seems to serve its purpose quite well. We'll see how it holds up in the next few years. Also with this project, we can easily see that the electric cars based on and powered by traction batteries are inherently fit for a battery swap or battery replacement technology. It would work even better if the manufacturers considered this when they design EVs, since a battery swap or replacement friendly car could help keep a car with zero emissions running on the road for a much longer time. This could also mean new business opportunities, from battery manufacturing and installation to the recycling industry and more. My next step is to turn the original 24 kilowatt hour battery into a stationary power source, and I will then try a new EV power system design after that. You are more than welcome to follow my progress here or on my blog at Hands on Deck, where you will also find some other projects I've worked on over the years. Finally, if you have any questions on the battery replacement project or you need help trying it yourself, you can contact me anytime. Thanks to my sister who patiently helped me take the pictures and the videos here, plus many more bloopers with bad takes, miswordings, and mistakes that will likely never see the light of day. Thanks. See you next time.